So continuing with our introduction to finite element methods, we will go with the strain displacement relations. Okay. So in this strain displacement relationship, we consider two-dimensional element which lies in the xy plane, which is shown in the figure. Okay. So when the force acts on the element, it undergoes deformation in both x and y direction. So it is shown in this diagram. Okay. Consider a two-dimensional element ABCD which lies in xy plane as shown in figure. ABCD is the two-dimensional element which lies in this xy plane. So when a force acts on this element, it undergoes deformation and it becomes A dash, B dash, C dash and D dash. So displacement in the x direction is U and displacement in the y direction is V. So we can see in this figure ABCD element, two-dimensional rectangular element. So after deformation, it changes its position to A dash, B dash, C dash and D dash. So this is deformation of element. So in general, the normal strain is defined as the ratio of change in length to original length of the body. So considering the element AB in the x direction, we have strain epsilon x is equal to A dash B dash minus AB divided by AB. Change in the position minus original position divided by the original position. So this is your first equation. Next, from the figure we can see that AB is equal to dx. AB is also equal to dx. So upon substitution, what happens? A dash B dash whole square is equal to dx plus d by u by d by x into dx whole square plus d by u by d by x into dx whole square. This is your equation number 2. Okay. So what we do is we neglect the higher order terms. It is d by u by d by x whole square and d by u by d by x whole square. So by neglecting the higher order terms, so this equation becomes A dash B dash is equal to dx plus d by u by d by x into dx. So after neglecting the higher order terms, so this equation is obtained. So this is your equation number 3. Okay. So next what we do is we substitute the equation number 2, that is this one, and equation number 3 in this equation number 1. So here we are having the values, so that what we do is we substitute it here, substituting equation 1.22. This is this one and 1.23. Equation number 1.1. This and this we substitute in this equation. So what happens if we substitute these two equations on this equation? It becomes epsilon x is equal to dx plus d by u by d by x into dx minus dx divided by dx. Upon simplification, what we get? We get dx into 1 plus d by u by d by x minus 1 divided by dx. So the strain in the x direction, epsilon x is equal to d by u by d by x. So similarly, considering the element AD in the y direction, so that is the strain in the y direction is epsilon y is equal to d by v divided by d by y. So the shear strain mu xy is equal to d by v by d by x plus d by u by d by y. So by substituting the shear strain mu xy is equal to d by u by d by x plus d by u by d by y. So that is for a 2D element. Similarly, for a three-dimensional element, considering W as displacement in the z direction, the strain displacement relations are obtained by extending two-dimensional analysis. That is, the strain in z direction, epsilon z is equal to deva W by deva z. So the shear strain is mu of yz is equal to deva W by deva y plus deva v by deva z, and the shear strain mu of zx is equal to deva u by deva z plus deva W by deva x. So next is the boundary conditions. So what is my boundary condition? So we must specify a boundary or a support condition for a structure model such as the assembly of the space, or k will be singular, that is the determinant of k will be equal to 0 and its inverse will not exist. This means the structural system is unstable. So we must specify the boundary condition for each and every problem. So boundary condition means so where the structure is fixed, so where what type of structure is it, and how is it fixed, which end is fixed, and where is the load applied. So all this comes under the boundary conditions. So without our specifying adequate kinematic considerations or support conditions, the structure will be free to move as a rigid body and not resist any applied loads. So in general, the number of boundary conditions necessary to make the stiffness matrix K non-singular, it is equal to the number of possible rigid body modes. So the boundary conditions are of generally there are two types. One is homogeneous boundary condition. So that is the more common that occur at the locations that are completely prevented from movements. So these are the homogeneous. These are called as homogeneous boundary conditions. So the non-homogeneous boundary conditions. So it occurs where the finite non-zero values of displacement are specified, such as a settlement of a support. So the main two types of boundary conditions are the homogeneous boundary conditions that are the most common, which occur at locations that are completely prevented from the movement, and the non-homogeneous boundary conditions which occur where finite non-zero values of the displacement are specified, such as a settlement of a support. So next is plane stress and plane strain. So this plane stress and plane strain basically it occurs in 2D problems. So this plane stress condition, so it is defined as the state of stress in which the normal stress sigma and the shear stress tau, which is directly perpendicular to the plane, and they are assumed to be 0. Okay. So here sigma x, sigma y, and tau xy is given by sigma x is equal to e divided by 1 minus mu square into epsilon x plus mu into epsilon y. Sigma y is equal to e divided by 1 minus mu square mu into epsilon x plus epsilon y. So tau of xy is equal to e divided by 1 minus mu square into 1 minus mu divided by 2 into mu of xy. So in this matrix form, we write it as this form: sigma x, sigma y, tau xy, e divided by 1 minus mu square 1 mu 0 0 mu 1 0 0 0 1 minus mu square 2 epsilon x epsilon y and mu of xy. So similarly, the plane strain condition, it is defined as a state of strain in which the normal to the xy plane and the shear strain are assumed to be 0. So here the sigma x sigma y and tau xy is given in this form, and similarly we write in the matrix form like this.